Hello everyone, welcome back. In this video, we'll be discussing about the last problem of biweekly contest, count of sub-multisets with bounded sum. The problem is very interesting, but unfortunately it is one of those problems where the author has put unnecessary strict time complexity, because of which even though your solution is fully correct, you will fail last few test cases. So I would say if you are able to pass 95% of test cases with your solution, no need to spend more time on this and you can move forward. So with that, let's get started. The problem states that you are given a zero indexed array nums of non-negative integers and two integers L and R. You need to return the count of sub-multiset within nums where the sum of elements in each subset falls within the range of L to R. And since this answer can be very huge, you have to return its modulus 10 to the power 9 plus 7. Now a sub-multiset is just a simple simple subset itself. It's just that the subset may contain more than one element. That's what they are trying to explain by this sentence. So let's take an example. Let's say nums is 1 2 2 3 and L is 6, R is 6. Basically we want the count of subsets such that the sum is exactly 6, right? So only one such subset exists here, which is 1 2 3. Notice that it doesn't matter which two you will take, because as per the problem statement, two sub multiset is same if sorting them results an identical multiset. So even though this, you can say that okay, I will take zero indexed first index and third index, or zero indexed second index and third index. If you sort both the sub multiset, you will get the exact same thing. So that's why it is only considered once, and hence the answer here is just 1, right? So hope the problem statement is clear. Now how to solve this? So as always, instead of solving the original problem, let's try to solve a simplified version first. Let's say the given array doesn't contain any duplicates. In other words, sub multiset is nothing but a subset, because the given array itself doesn't have any duplicates. So you need to find out the number of subset that sums up to a particular sum, right? And if you're not able to solve this, solving the original problem would be difficult. So let's look at this. So we need to find out the number of subset in this particular array that can sum up to 15, right? So what you will do, let's take 0th element. Either 0th element will be in your subset or it will not be in your subset, right? Only two things can happen with the 0th element. So if it is in the subset, what you will want, you want the number of subset that can sum up to 14 starting from index 1, right? Because you already took 1 in your subset, so remaining sum that you need is 14. So you need to find out the number of subset that will sum up to 14 here, and whatever subset you will get, you will simply append 1 to that subset and the sum will become 15, right? The second choice could be uh, you will not include 1 in your result. If you don't include 1 in your result, you will need the number of subset that can sum up to 15 starting from index 1, right? So isn't these two problems exactly similar to the original problem? Original problem was find me the number of subset that sums up to 15 starting from index 0, right? The reduced problem are find me the number of subset starting from 1 that can sum up to 14, that was the first one, or find me the number of subset starting from 1 that can sum up to 15, right? So hope you can see the recursion here. So what we will simply do, we'll simply have some function f which will take two things, I and sum, right? and this will return the number of subset starting from index I that can sum up to s. You can simply recursively call this function for a particular index I and you will get the answer, right? So let's look at it. Let's look this same example and do a try run. So we have this same example, and we wanted to find out the number of subset that can sum up to 15. Now we will start from 0, right? We wanted to find the number of subset that can sum up to 15 starting from index 0. So we called f of 0 comma 15, right? Remember, the first index is the first number is the index, second number is the sum that we want. Now as we discussed, there can be two possibilities. Either the 0th element will be there in the subset or it will not be there. So if it is there in the if it is not there in the subset, what you need the number of subset starting from index 1 that can sum up to 15, because you haven't taken anything, so the sum remains as it is. So that's what we will find out, f of 1 comma 15. If it is there, then we need to find out the number of subsets starting from index 1 that can sum up to 14, right? Now once you have the values of f115 and f114, you can simply sum them up and that will be the result of f015, right? Now how to find f115? Again the same thing. You are starting from index 1, so you will say, okay, for index 1 there are two choices. Either index 1 will be there or it will not be there. If it is not there, then the sum will not change. So we wanted a sum of 15 starting from index 1. We will want sum of 15 starting from index 2 as well, right? So f2 of 15. If it is included, then we have included index 1. It means we have taken a number which is giving us a value of 2. So we want the subset which can sum up to 13, right? So in the similar fashion, you can figure out f1 of 14 and f others as well. So this is the way in which recursion will proceed, and you can see there are duplicates when you are trying to evaluate a particular state. So when you are trying to evaluate f1 of 15, you have to evaluate f3 of 12, and similarly if you are trying to evaluate f1 on 1 of 14, you have to evaluate f3 comma 12 as well. So because you may have to evaluate same state again and again, we can memorize this. Basically we can store the value of a particular state, and whenever we are asked to calculate the value of that state, we will simply reuse whatever we have calculated before, right? Simple memorization technique. So how would the pseudocode look like? The pseudocode is very straightforward. It will be something like this: f of I comma index, which is giving us the number of subset that can sum up to this particular sum starting from this particular index. Now as we discussed, there are two choices. We'll come to this later. There are two choices. Either we will not include the current element in the subset. In that case, we'll simply want the number of subset starting from the next index that can sum up to the given sum, or we will include the current index in our subset. If we are including the current number in our subset, we will simply say f of index plus 1 comma sum minus array of index is the remaining sum that we want. Now this taking a particular index, you can only take that index only if the sum allows you, right? So that's why this if condition is there. Now you will simply sum these two things up, and finally you will store this in your DP array. Now whenever you are asked to compute any state, instead of directly computing the state, now you will add one more stage wherein you will check whether you have already computed that stage again previously or not. So you can simply fill everything with -1, which can denote that you haven't computed the state. if you have computed the state, you will have some positive value. So if it is -1, if it is not -1, it means you have already computed the value. You will simply return from the DP array. Otherwise you will compute. The base case is straightforward. If you have exhausted everything, like if you have considered all the indexes in your given array, and in that case you can only make a sum of 0, right? Basically you can't take anything, so you only can make a sum of 0. So if sum is not 0, you will simply return false or 0. Number of ways is 0, right? If sum is 0, then you have one way, right? So this is the overall solution. What would be the time complexity? The time complexity will be straightforward. Number of states, right? Because each state you are computing exactly once because of this DP array, multiplied by what you are doing inside each of these state, right? So let's answer it one by one. Number of states. What is the number of unique value of index? N. And how many unique value of sum can be there? Let's say S. S is the given sum that we are asked to compute. Now these many different ways F can be called. Now inside each of these state, what you are doing, you are simply calling one function or two function based on some value. So basically you are doing order one operation here, right? So the overall complexity is n into s, where n is the size of the array and s is the total sum, right? Now let's look at the given problem's constraint. The problem constraint says that nums.length is less than equals to 2 into 10 to the power 4, and it also says that the sum of nums will not exceed 2 into 10 to the power 4. So basically, as per the problem statement, the given array sum can be 2 into 10 to the power 4, right? And s can also be 2 into 10 to the power 4. So if you multiply them, this will not pass. But notice this statement, sum of nums doesn't exceed 2 into 10 to the power 4. What does this mean? This means that if you think about it, you only have distinct elements in your given array, right? So the sum is 2 into 10 to the power 4 and you have only distinct elements. So how many elements you can have that can sum up to this, or how many distinct elements you can have that can sum up to this? You want this to be maximum possible set of numbers because we want to compute the maximum value of n here, right? So how many maximum distinct numbers you can sum such that the sum is this? So the best possible thing would be to just sum up 1 2 3 4 all the way up to sum x, such that if you sum them all up, it is 2 into 10 to the power 4. So if you simply compute this value, it would be x into x plus 1 by 2. So let's assume that x is also equals to x plus 1. So basically it is x plus 1 whole square, just for simplicity. So x plus whole square equals to 2 into s, right? So what is the value of x? X would be root 2s. In other words, you can have only root 2s distinct value in your given array, right? Or in other words, the value of n, even though it is given that nums.length can be up to 10 to the power 4, because of this statement, nums.length is restricted to root 2s. And what is the value of root 2s here? S is given as 2 into 10 to the power 4, and if you multiply by 2 and take a root, it will be coming as 200. So not exactly 200, but because we have taken some approximation here, but maximum value would be 200. So in this case, even though the value of n is 2 into 10 to the power 4, the actual value of n is 200. So the complexity is 200 into s, which is sufficient to pass the given time constraint, right? Now this entire thing, we just have figured out how many subset are there which will sum up to a particular sum, but problem states that you need to figure out all the subset that can sum up to any number between L and R, right? So basically this sum itself can be anything between L and R. So you not only want, let's say L is 15 and R is 19, right? Or let's say 20. So what you want is you want f of 0 comma 15, right? Number of subset that can sum up to 15. You also want f of 0 comma 16, right? Number of subset that can sum up to 16, all the way up to you also want f of 0 comma 20, number of subset that can sum up to 20, and you will just sum them all up and that will be your final answer, right? So we does this change anything? Like if you are computing these many states, does this change the time complexity? At first look you might say that okay, previously we were computing only one f, but now we are computing like r minus l number of f's, so the time complexity will multiply by r minus l. But this is not the case. Why? Because notice that this 200 into s already took care of all possible values of index and sum. So 0 comma 16 is already computed, 0 comma 20 is already computed, and whenever you call this function for an already computed value, you will be hitting this particular if condition, and you will simply return that stored value without actually computing anything. So all of these further would just be an order 1 operation, not a order n into s operation, right? So the complexity is still 200 into s and is good to pass the given time constraint. Now if you haven't understood any of the piece till yet, I would strongly encourage you to rewind and watch the past 5 to 6 minutes of the video before moving forward, because the next part is just simply an extension of this piece. So if you remember, we simplified the problem by saying that the array doesn't contain duplicates, and because of which sub-multiset translates to subset. But now let's tackle the condition where this array can contain duplicates. Basically it can have more than one element which are same. So in this case we can see there are more than one ones and some twos are also duplicated. So what is the difference? I would first encourage you to pause and try to think whether you can apply the same algorithm that we just discussed in this situation or not, and if not, why not, right? I would strongly encourage you to pause for 5 minutes and try to think the difference in this problem and the original problem by yourself. So hope you thought about it. The difference lies in the fact that previously all these 4 things were a different array or were a different subset, but now all of these 4, and there can be many more as well, are exactly one subset and will be counted exactly once. So previously you were thinking that okay, 0 1 and 2, this 3 subset which will form by these 3 indexes. Now 0 1 and 5 subset which is formed by these 3 indexes, 0 4 and 5 and 0 6 and 5. So all these subset previously were different, but now if you see all these subset currently like values of all the subset is exactly 112, right? And hence all of these are exactly same. So in previously they were counted 4 times, but now you have to count them only once, and that's the major difference between this problem and the original problem, right? Now how will you tackle this? So previously whenever you reach an index, you take the decision whether to take it or not, right? So basically you had 2 choices from that index, and if you have 2 choices, let's take simple example, let's say an array contain 111, right? That's the array. Let's forget about this array for now. If in this array, how many subset you will have that can sum up to 3? So if you say okay, I will take this, like at every index I will have 2 decision, either I will take this or not take this. So if you say from the first index I will either take it or not take it. So if you don't take it, you will have a sum of 3 or sum of s, let's say, which starting from index 1. Similarly, if you take it, you will have a sum of s minus 1 starting from index 1, right? Now if you, from this index again, you have two choices: either you will take it or you will not take it. So if you will take it, let's say you don't take it, if you don't take it, you want starting from index 2, I want a sum of s. And if you take it, you will say starting from index 1, starting from index 2, you want a sum of s minus 1, right? Now think about it, this is nothing but a sum of this and this, right? So you can say the value of this state is simply the value of this plus this plus this, right? Now see, this state is computed twice. Number of what we are saying is we have taken 1 1 here. Here also we are saying we have taken 1 1 here. But this was the 0th index and this is the first index, and because of which we are left, like our subset currently contains just 1 1, and we wanted to find out a subset that can sum up to s minus 1. So these two states are exactly similar, but we will be adding it twice in our result, and because of which our answer will increase, right? So this choice of whether to take or not take is something you can apply across different element. But if you try to apply it on the same element, there will be cases where if you take the same element at the first iteration versus if you take the element in the second iteration, they will be considered a different subset, but you don't want that, right? And that's why if you have a series of same element, you will not say that I will treat it as individual element. Instead I will say either I will take no ones, or I will take 1 1, or I will take 2 1, or I will take all the 3 ones. These are the only 4 states that can happen from this 4 elements. But if you take everything just like take not take thing, you will have total 8 states possible, right? So that's the major difference. Basically, when we will be applying the same algorithm. Only thing that will change now is whenever we have a same set of elements, we will not classify as take not take thing. Instead we will say I will have only x number of choices if the given series of element contain x minus 1 elements, right? So what we will do, initially we will convert this given array into something like this, right? So we'll say 1 occurs thrice because all these 3 we have to combine them in one shot. Similarly 2 occurs thrice, so all these 2 we have to combine them in one shot, and 4 occurs once, right? Now we will apply the exact same algorithm. So let's look at it. So how it will proceed? The same thing, we want the sum all the way up to 15, right? And I have just changed the frequency of 4 here to make things a bit more clear here, but you can apply it on any frequency array as well. So let's say we want to make a sum of 15 starting from index 0, right? So this is the index 0, 1 and 2. Now as we have discussed, this 1 has a frequency of 3, right? So what will be a choice? Either you will take no ones, or you will take 1 1, or you will take 2 ones, or you will take all the 3 ones. These are the only 3 choices you have, right? And if you take 0 1, you will lead to f of 1 comma 15, basically the number of subset starting from index 1 that can sum up to 15, right? In the same fashion, if you take 1 1, you will be ending up at 1 comma 14, the number of subset that can sum up to 14, and 2 1 1 comma 13, and 3 1 1 comma 12, and you will simply sum it all up to get the final answer of f of 0 comma 15, right? Now in the same fashion you will continue. Let's say you want to find out f of 1 comma 15. You will say that I have two 2's here, so I have only three choices. Either I will take 0 2, or I will take 1 2, or I will take 2 2. So if you take 0 2, you are not contributing anything to the sum, so sum remain as it is. You want f of 2 comma 15. If you take 1 2, the sum will be decreased by 2, so you want f of 2 comma 13. Similarly, if you take two 2's, the sum will be decreased by 4, so you want f of 2 comma 11. And in the same fashion you will keep on continuing and calculate the further results. So hope the entire thing makes sense. Now let's look at the pseudocode. The pseudocode is exactly similar. Only thing that changes, instead of first of all we will prepare this kind of array from the given array, so that we have all the numbers with our same in under a single umbrella, so that we can avoid this sort of mistakes while applying the algorithm, right? And once we have this array, let's say val contains, we have two arrays. First one is val, which contains the actual value, and second is f, which contains the frequency corresponding to that particular value. Now everything else will be same. We will start from index comma sum. We will just to one more fact, we can see that it also has duplicates, right? F of 2 comma 10, f of 2 comma 10, right? So we can get duplicates here as well, and to avoid recomputing the values for duplicates, we will do memoization, right? So memoization is still there. Memoization is exactly similar. Basically, if it is not -1, we will simply return it from the dp array. Otherwise, previously it was take or not take. Now we have these f of index plus one number of choices, which is either you will take it once, either you will not take it, you will take it once, you will take it twice, all the way up to f of index times. And for each of these you want the number of number of sub-multiset that can sum up to the remaining sum. The remaining sum would simply be sum minus cnt multiplied by value of index. Now you will simply add them all up, and finally answer will contain the number of sub-multiset which can sum up to the given sum, right? Now what is the time complexity? Time complexity, if you think about this, we already had discussed the time complexity of this one, which is coming to as 200 into s, right? Not n into s, 200 into s, right? So number of distinct state here as well would be 200 into s. But now what we are doing inside each of these state, previously it was order 1 because we are just doing some mathematical operations, but now we have a loop here as well that will iterate over f of index number of times. So in first go it might see that okay, a factor of f will also be multiplied, where f can be the frequency of an element, and a frequency of an element can be all the way up to n. Let's say the number is 1, so 1 can occurs 2 into 10 to the power 4 times itself, so the frequency of element can be very huge, so this entire thing may not pass. But what if I say you, if you find out the amortized complexity, like if you actually write out the recursion thing and see the number of states you are computing and the operations you are doing inside each of these state, it will still be 200 into s rather than 200 into s into something, right? How? I would encourage you to pause and try to think for a moment. So the solution is simple. We wanted to find out the total cost of this function across all possible values, right? So let's assume this array itself, basically we have 3 distinct indexes and the sum is 15, right? So what we would want, we want the cost of each of these values in terms of this loop, right? Because this is the only loop that is not linear, that is not constant. It is it seems to be linear. So what we want is cost of f of 0, 15, f of 1, 15, 2, 15, 3, 15, and then 0, 14, 1, 14, 2, 14, 3, 14, and all the way up to 0, 1, 1, 1, 2, 1, and 3, 1. Now what is this particular cost? This is basically what you're doing. You are in this, you are iterating over some f of 0, which is the frequency of the 0th index. You are iterating over f of 1, the frequency of the first index. You are iterating over f of 2, the frequency of second index, and you are iterating over f of 3, the frequency of third index. What this entire sum would be? This entire sum would simply be n, right? The total frequency, the total count of element in the given array, right? Nothing more than that. So this will be n, and in the similar fashion this will also be n, and in a similar fashion this will also be n, and all the way up to here. So everything is n all the way up to all the way down to f of 0 comma for all the way up to down to when s equals to 1. So total complexity is n into s here, where n is the total number of elements in a particular array, right? Now one more thing to look at here is n into s will seems to don't pass, but if you see this n will, like, every time you will not have all these n elements. Basically if you have all these n elements, you will not have other elements in this place, right? So overall you can actually, this is the actual time complexity, and you can apply this entire thing for all the way up from L to R. And we already discussed that if you call this function with different sum, it will not matter because we have computed the overall time complexity. So this is on the edge of passing time complexity, and that's where I was referring that the author did a good job in setting the exact time complexity, because the same solution may or may not pass across depending on how you are implementing it. So I would encourage you to implement this solution by yourself, and if you are able to pass more than 95% of test cases, you can just skip it and move forward, because this is the crux, how the complexity in amortized form is n into s. So next we'll be looking at the code. The code is exactly what we have discussed. So we have this ways array, which will give you the number of different sub-multiset that will start from in this particular index and can sum up to this particular sum. So what we are doing, as we discussed, we will first build this 2 array. If you remember this 2 array, right? So we have a vector of pairs array, which whose first element would be the value and second element would be the frequency. Now for everything between L and R, we are simply calling this ways function for 0, j. Now this ways function, if you think about it, this you can remove. I think I added it for some other reason, because I haven't added a check here. So this part is just a safety check. This is the base condition, and then we have this memorization thing here. After that we are saying either we will take 0 or 1 all the way up to frequency number of times the current element, and based on that the sum will also change. So this is the overall algorithm. If you have any doubts in this particular piece, feel free to follow up in the comment section below. Again, it may or may not pass given how you are implementing it. This solution seems to be passing sometime and sometime it doesn't. So we can optimize some of these things here, like remove the sum 0 by adding a while loop instead of for loop here, or you can simply remove this modulus mod with a minus mod in case the number is greater than a particular number, and so on and so forth. You can do some optimizations here to make it pass, but I would say it is not that worth, because this is the crux, and if you are able to decode it, that should be good enough and you should move forward. So with that, if you have any doubts in this video, feel free to post them in the comment section below. I would be happy to answer. If you like the video, give it a thumbs up and do subscribe if you haven't already, and I will see you in the next one. Thank you.